To motivate this work, let's start with the vehicle routing problem, whose objective is to define paths for vehicles that must visit pickup and delivery locations. Um, Once this problem is solved, we can then obtain the optimal solution, which shows here three different routes for vehicles to follow so that the total distance that's covered by them is minimal. Now, something of interest to us is what is the largest variation in these locations of each of the points that still has this route remaining feasible. That means the time windows are met, if there are any charging requirements, they are satisfied, and the defined optimal solution still remains valid. Another case is power generation, where you have these different generators and demands that have to be met in this power grid, but two of the generators are then replaced by renewable sources, which mean we don't have control over how much power is being injected. So in this case, something of interest is what is the safe range of renewable power that can be injected. In both these scenarios, we're interested in what is the range of parameters that can be varied before some undesirable outcome occurs. To illustrate this, let's consider that the origin of this space that is defined by xi is defining the nominal point where there is no change in any of the parameters of the system. Now, if you go to some other point here, then along axis xi1, there is some change in the system, and along xi2, there's some change in the system. So the original parameter p has now been updated to p plus xi based on its position. When we're searching this space for what is the range of variations that is feasible, we define some limit on what is the search space to be explored so that we keep things reasonable. Now, there is a safe region. The nominal point is assumed to be within the safe region, and some parameter variations around this remain feasible, while outside of this safe region we then have system failure or degraded performance. So what's of interest to us is to then precisely define this boundary that is defined by partial S, also called the feasible operational envelope or the decision boundary, which separates the safe and unsafe regions. In literature, design of experiments is one of the approaches that is used, but this suffers from designer bias and poor scaling because it is based on the prior experience of the expert, who then defines what are the scenarios that have to be tested. This is automated by active learning, which uses some support vector machines or Gaussian process regression to then define what is the next location to be queried. But it results in wasted queries because it is not always that the points that are being queried will happen to be along the decision boundary. Also, no method in literature guarantees the localization of the feasible operational envelope within some defined acceptable tolerance. But in general, points are queried in the space, and then some black box function, a classifier, will then provide you the output as that query point is at an undesirable location where there's some failure, or it is at some desirable location. The problem is that if we try to randomly query along the space, these evaluations can be expensive, and ideally we want that all of the evaluations happen along the boundary. Also, we want to guarantee that the points that are provided as the output should be within some user-defined tolerance so that we can capture the criticality of how important it is to localize the boundary within some tolerance. So, accurately localizing this partial S within the user-defined epsilon neighborhood with high sample efficiency is our objective in identifying this boundary for a black box classifier function. To do this, we start with bisection. We know that the nominal point is going to be feasible, so we have to start by finding some infeasible point, which then means that there is a partial S, that is a decision boundary between the 2 points. So we can then apply bisection to then localize the boundary to within an epsilon distance between the infeasible and feasible points. Once we have that, we can start the decision boundary walk, which essentially queries the intersections of epsilon radius circles that are centered along the last feasible and infeasible points. So in this case, these 2 points are obtained from bisection, and then we look at the intersections and query one of the points. So we can choose the negative cross product as the direction sense that we will follow. So in this case, we query this point, we find that it is infeasible. Now we shift the center of that infeasible circle to this new location. Then we look for the intersection, and again at the negative cross product we query that point, we see that it is infeasible. Now we shift it again and we query the next intersection point, we see it's feasible. So now that feasible circle center has been shifted to this location, and we keep doing this, and in doing so we are essentially localizing that decision boundary, because between any two of the sequentially queried points we have a decision boundary between them. So the first pair of points that are queried, they have a distance less than or equal to epsilon, but after that the intersections were using the epsilon circle, so they are at a defined distance of epsilon between them, which guarantees that these points are then within a distance of epsilon from the decision boundary. As for termination, as the exploration continues, we keep checking how far is the first set of points from this query point. So if we find that the original the starting points from the bisection are within that circle of epsilon radius, then we have arrived back to the starting location and we can then terminate. So this algorithm, called the Epsilon-Neighborhood decision boundary governed estimation algorithm, or EDGE, it localizes the boundary within its epsilon neighborhood, and we can see this for the Goldenstein price function. So the nominal point is known to be interior. We can start by testing the 4 corners. In this case, if we test this corner, we see that it is an exterior point, and so then with bisection we can localize to the epsilon neighborhood, and running the EDGE algorithm results in the definition of the inner approximation and the outer approximation as shown along the boundary. We see similar behavior for the Rosenbrock function and the same for the Beal function. You can notice that it captures the nonlinearity of the test function pretty well. So the EDGE algorithm requires no hyperparameter tuning, and because of this it can be applied as is to black box functions, and it guarantees the epsilon neighborhood localization, and every queried point contributes to these approximation sets outside of the initial bisection points, which is a set of wasted queries, except for when the final pair of points has been found. Comparing this with some other algorithms, grid sampling is a method of searching along the entire space of possible parameter variations using a grid cell of size epsilon. Now by looking for the points that have adjacent pairs of infeasible and feasible points, we can then localize the decision boundary to be within them. A metric that we can use to then compare the localization accuracy is the average symmetric distance. So this tells us how good is the localization by comparing it with the true decision boundary, which we know in case of these functions. So between the EDGE algorithm and the grid sampling, we see that the grid sampling does marginally better in terms of the localization because the error is lower, but the sample count is significantly higher. So in comparison, this naive approach is highly sample inefficient. Another approach is active learning at the boundaries, with the key idea being that we start with randomly queried points through that space of parameter variations, and then these points are then sent to a support vector machine, which then uses their labeled sets to then predict the boundary that separates the feasible and infeasible points. Now once we have this boundary, we then query along the boundary using a diverse set of boundary points to then continuously update the boundary estimate. And as you can see, the estimate starts to resemble the true decision boundary. However, one drawback is that you can see that there are queries that are happening in regions far from the decision boundary, which results in wasted queries. If we compare the accuracy, the localization error for the same sample count as EDGE is much higher, which means that it is not as efficient as the EDGE algorithm. Also, the ALB, the active learning at the boundaries, has significant stochastic behavior because of how it is initialized. And also it requires hyperparameter tuning, which makes it less suitable for black box functions. Across different test instances and repetitions that is provided in the paper, you can see that the edge localization error is always lower than the ALB boundary localization error. And for the same sample count, you will see that the ALB computation time is much greater because of the time required for training the support vector machine. Now, applying this algorithm, the edge algorithm, to a power grid problem, we see here the problem formulation, which is a DC optimal power flow problem, where the objective is to minimize the power generation cost while accounting for nodal balance, power and transmission limits, and line susceptance and voltage angle difference limits. So in this example, we look at a 5-bus case from IEEE with the parameters that are defined for the maximum power that can be generated by the different generators, the demand or the load at each of the buses, and what is the line parameters that define how the different buses are connected to each other. Once we solve this with Gurobi, we then find the variables, the optimal solution, which involves the voltage angle at each of the buses, the power that's being transmitted, and the power generation. So we can consider this as a nominal point. So there is a feasible point which provides us with the lowest power generation cost. And if we now replace some of the generators with renewable sources, what happens then is that the power is no longer in our control, and it acts as parameters that are being that are injecting power into the system. So we want to know what is a safe range of renewable power generation. And if we apply the edge algorithm, then starting from this nominal point which is feasible, we then find an infeasible point, and then the bisection line results in these queried points here, after which the edge algorithm then moves along the boundaries and then finds the true decision boundary with high accuracy. Now we see a linear pattern here, and the reason is because we use the DC OPF, which has linear constraints. So we do see that behavior here, even though the edge algorithm had no access to the defining problem. So in conclusion, the edge algorithm, it does not require any hyperparameter tuning. It allows it to be applied to any black box classifier, and it guarantees epsilon-neighborhood localization accuracy while outperforming the state-of-the-art active learning methods and the grid sampling method, which provides epsilon-neighborhood guarantees. In future work, we need to extend this to multi-class problems, so problems where the classifier doesn't just provide 0 or 1, but multiple sets of classes, and high dimensional parameter spaces. As you can see, this has only been implemented in 2-dimensional space. Further, the epsilon-neighborhood definition allows us to apply this to stochastic systems where there is measurement or system noise. And finally, the edge algorithm provides an output of approximation sets, which are essentially the support vectors, which can then be used to improve the training of the support vector machine. This QR code provides the paper with all of the mathematical rigor and the results in detail. This concludes our presentation. Thank you, and I open to any questions or comments.